Okay, record is on. So today we start with practical tasks in Matlab. So it means that you need a Matlab and Matlab simulation environment Simulink. In this case, there are two options for you. First of all, you could come here every Monday to the computer class. We have Matlab here, and you could, how to say, make your practical tasks here. Second option, you could install Matlab on your personal laptop and to do all of this at home. And as an alternative, there is one more similar to Matlab program with the name Stilab. Okay, I'll write its name in the chat. It's Stilab. And its simulation environment Xcos. But for Matlab, we have 3 ready-made schemes for, how to say, your analysis. But in a Stilab, it means that you need to develop these schemes by yourself. I have an example how to do this for the first one, but it should be improved, and I don't have an example for the second and third. So this depends on you. What is more feasible for you? So decide yourself, yeah? But as I said, today we start modeling, or in other words, your practical tasks about power system control in Matlab. Okay, here it is a Matlab environment. These are 3. Okay, we have one more student, so I think I need to repeat one more time. So today we start practical tasks in Matlab environment Simulink. So it means that you need this Matlab program to do these tasks. How this could be done? First of all, you could come here every Monday in the room 318. Yes, because there is a computer class, and with a Matlab, you could do all these tasks here. Or as you wish, you could install this Matlab by yourself at your personal laptop and do it at home. If you don't have possibility to install a Matlab, you could use open software with the name Stilab and X simulation environment Xcos. It is very similar to Matlab. But for Matlab, I have ready-made schemes for first 3 tasks. And for Stilab, it means that you need to do it by yourself. I have an example how to do the first one. Okay, this is what do you need. Okay, now we have a Matlab, we have this environment. I have a special map with, okay, open it. Okay, for the first 3 tasks. Total, you will have 4 tasks. Here we got 3 tasks. I'll put all these materials, no, schemes, yes, with pictures. This is picture for a scheme, yeah. I put these schemes in Matlab in Ortus, so you could find all this information in your Ortus. Okay, it is empty now, but I'll put all this information here in Ortus today, so you could find all you need. And now I'll open this scheme number 1 for the first task. Okay, maybe I need to open a Word document. New Word document to write up comments for you to be easier. Okay. So first of all, what do we see here? Okay, this is for my comments for you. This document. What do we see here? Here we can see two similar schemes for the concentrated power system. It means that we have one united generator to be easier to understand. I can use paint as well. So what do we see here? Here, of course, we have a scheme with transfer function. And it means that if you don't have basic knowledge about the control systems theory, about the transfer functions, it is very useful for you, yes, to find any information about transfer functions, yes, and to read it by yourself. Because these are basic knowledge. This is basic knowledge, yeah. Okay, so what do we see here? I tried to explain, yeah. So the idea is that we have a concentrated power generator, yes. So all generators are united into one big generator, and here we got a load. So okay. Okay. Maybe you could use this is a this is an old description in Latvian, but okay, you see this picture. So what is the idea? So we simplify for the first task power system as simple as possible. So no specific elements such transmission lines, transformers, substations, and so on. Only one concentrated generator. This one is for this first task is hydropower plant, HP, and a united load, so one load. How it is implemented, how it is modeled here. What do we have here? Okay, first of all, here we have two transfer functions, this one and this one. Two transfer functions that represents this power generation. Why we have two transfer functions? Because we have two main elements, like I show you in the first lecture. Okay, I think I could open it in a book because maybe you don't remember. This could be more easier. So it could be, okay. It was, no, it was in September. It was in September. Okay, this one. I'll open to show you. If you don't remember. This close. Okay, I need to wait for the screens, yes. Come on, okay, yes, this screen I showed you, yeah. So the idea is that this scheme, yeah. So power system, generator, turbine, valve, yes, water, valve control, turbine rotating, turbine rotates generator, generator produce electricity. Control, rotating speed control. This negative feedback. Go back. What do we see? These two elements. This one represents this element represents the valve, because we open close the valve with, yes, to control water flow, and this one is a turbine that produces electricity. No, rotates generators, as a result electricity. These two elements. This element is from the control theory. Transfer function is quite complicated, but it's specially designed like the real turbine is. So it is, yes, complicated. It's a mix of different basic transfer functions connected together. But all others transfer functions are very similar. This is the picture. Oh, okay, real element is here. Here it is. There's transfer function, yes, real elements, but from a Simulink library, yes. But for you to be clear what is it, yes, it is, how to say, a picture, yeah, to show you the name of this element. This is 1 divided by TS. No, it means it is Laplace operator, yes. It's from this theory of transfer function theory. It means what the transfer function is, yes. So how to represent this valve reaction, yes. This is an elastic feedback for smooth operation. This one is you see, a regulator, yes. So this one represents the inertia of power system, the speed of reaction. It is inertia. That's why we see the known Tj elements that is present here is in seconds to represent inertia, power system inertia. And as a result, there is this feedback is the static regulation. So we understand that if we have power, okay, frequency. Here we watch the frequency. What is the frequency? Yeah. So frequency deviation is the same. We have power deviation. Yes, frequency, it's a signal. Our information about power deviation. Yeah. So, and this is static regulator that understand what the deviation, how much power do we need, more or less, from the generator. Yes. So this is static coefficient. Yes. In here it is represented in a percent. So it is typical that for static regulators or for hydropower plants, for CHPPs, yeah, combined heated power, yeah, it is from 3 to 7% approximately. So this is the regulator. And this one, D, is the coefficient that represents the load reaction. So we discussed previously that there is a generator reaction on power balancing and system, and at the same time there is the same, that is like a mirror reaction, yeah, the load reaction on the frequency deviation, because frequency is a power density for the load, yes, because we have a sinusoidal power, because we have sinusoidal voltage and sinusoidal current, yes. So it's a density. That's why here we have main parameters. So here, this is the inertia of a power system in seconds. Here is a coefficient of a load reaction. Basically, this coefficient is up to 2. Yes, it's in it's unnamed units. Yes, so it's because it's a reaction coefficient. Yeah, so it is up to 2. This is the load. This is not. This is a power a power, how it calls, a power shortage. Okay, so this is a power shortage that could appear, because here we will see what is the reaction on a power deviations. Yes, about the about the deviation in a power balancing. Yes, so this is our tool how we could make this deviation. So here we change, we decide in a what time, yes, in the simulation process, and in how big. Sorry, this is sorry, I'm wrong. This is in second. This is in second in the time moment of this shortage, and this is the value in a percent. Yes, how much? How big is the deviation? Yeah, and this is the initial situation, so the balance. Yeah, 0 is a balance. Okay, now I'll write all this important information for you. What do you need to know? Okay, so okay, this is a picture. Okay, but maybe I'll use pictures for you. Maybe it will be more feasible, because I suppose that you will do it at home. But as I said, as you wish, that means I need to make a more detailed description for you, I think. Okay, next. I can okay, so this is a first, no, this is a second. This is the first one, yes. Let's see. This is a water. This is okay, so I need to import. Okay. Is it possible? Is it possible to make such a move? Yes, it is possible in this version. Oops. Okay. Due to some moments, some corrections, so I need to position. I need to make this. Oops. Okay. This version. Okay, so and for this version, I can use some more. Okay, whatever. Come on. Okay, so I think I can do more easy. I need all of this formula, so I can do this. Okay. Yes, I want all of them. I need all of them. Okay, I need all of them. And I need to call them wrap. I need this one. Okay, so nope. Okay, I need addition. Okay, I can't make this row, but not a problem. One by one. One by one. Number is not big. Number is really not big. Number of elements. Number of elements is not so big. D. Okay. Okay, so come back to scheme. Okay, this one is just a transfer coefficient. It's not needed in the description. It exists and it's enough for you. Okay, let's start with this position. Okay. Okay. First element. This is this transfer function represents a valve. Okay. TS, you understand, it's a hydropower plant, and to open and close the valve, we have an electrical motor. If we have a signal, open or close, we need some time for mechanical move, yes, to open and close. This time determines, yes, the time of reaction of this electrical motor, the time of this task, yeah, reaction time of a valve motor. Of course, it is in seconds. Okay. Next, what do we have here? Here we have power shortage. Power shortage to variables. Time of appearance in seconds and amount in percent. Of power. Okay, whatever. Okay, for this one, we do not need, don't need any changes. So for your experiments, yes, you don't need to make any change in these transfer functions, but this is mm, the flexible feed. Okay, the next one is power system inertia centered in seconds. Inertia, sorry, inertia. This is the this transfer function represents a turbine. Do not need to make any changes. Okay. This one here for the second scheme, but okay, I can write for now, no problem, is transmission line. The transfer function transmission line. Transmission line PM power. Okay, the next one is static regulator. S is static coefficient. Basically, it is from 3 to 7, not more. Okay, I forgot how this word is correct. How it is in English? Coefficient. So efficient. Okay. Forgot one F for efficient. Okay. Next one. Next one is this PT. Balance of power system 0 is in balance. I'm sorry, motor valve. Of motor valve. D is load reaction. So efficient. Okay, it's maximum value. Okay. I don't have a permission. Okay, no problem. Problem. Oops. Not responding. Okay. Okay. This PC. Okay, let's save here. I hope I could find. Or I can save in documents. I think. I hope my documents. And I should have a Matlab. Okay, I can save here to send you later. Okay, so tasks. So what task do you have? What task do you have? So you have two equivalent schemes. So this is one, this is the second one. They are the same, similar, equivalent. Here we run the program. Here you see running, ready. And here we have the watching windows. We are interested in a frequency. So this is the system inertia. It means that here we got a frequency. Okay, here could be very interesting to watch what is inside this block. Here because what is going on? It is in balance, it is 0. This is in percentage, so means from 0 to 1. Shortage means deviation. This is the reaction of this deviation, but it means that we have these deviations, yes, from 0 to 1. Balance is 0 to 1 is 100%. It means that all we got here is some values from 0 to 1, but we need to convert this to a frequency. How this could be done? Very simple. Okay, I can open it. Okay, very simple. What do we have here? It's a transfer function of the inertia. It is clear. Here we multiply this deviation to a 50 and sum with a basic frequency of 50 hertz. So here we have the deviation with a base, so not from 0 to 1, but from 0 to 50 deviation, and sum it to a 50 because we have negative deviation, so of 2 hertz with the basic of 50, it means that real frequency is 48 deviation. So one more time, we have deviation, negative deviation of 2 hertz with the basic of 50. The result here we got 48 hertz. And here what we have, it's a monitoring window. This one, double click. Okay, it is open. And now what we see here, this XS is time, modeling time. Here we have modeling time, 50 steps. No, 50 seconds, we could say, yeah. And this one, XS or YS, YS. Oh, I'm sorry, I have a call. Okay, so yes, continue. And this Y or Y X is the frequency. And here we could see this deviation, yeah, frequency deviation. Okay, but now here we see only one curve, the blue one. But we have here two schemes and two connection. F1 frequency 1, here it is, and frequency 2, here it is. So there should be two curves from each scheme, but the values are the same, and as a result we see only one curve. If we make any change, for example, here we could see the inertia is 8.5 seconds, and here we have the inertia the same, but we could put, for example, 10 seconds and run the program. It is ready. Now we will see why do we have such okay, it's okay, I see it's a lack of time. Okay, it is a tracer. Okay, we don't need a tracer, we need to do this, please. Okay, so what's so strange? What I have done wrong? 10, 8 for point. Okay, let's. It's just a question in this. Okay, yes, it's as I understand, it is a question in a. Okay, in a view. It's a view window. Okay, mistake. What is this? It was executed. Okay, it was executed value. Let's try one more time. Okay, yes. Well, now it works. I just pressed the signal, it was executed. That was the issue. I don't remember any, how to say, features in this version of old Simulink because I work for now in a new version. Okay, let's put 10 seconds. It's ready, and now you see we have this. We have difference two curves. We see the yellow one and the blue one. Okay, and here, for example, we could put 7 more. And here you could see. And your task is to change by yourself all these parameters. Yes, what is possible to change, to see what is the result, what is with a frequency, and describe what you see and why does this different appear. Okay, let's try to talk in short some moments. Okay, I'll put 20 seconds. This is here 5 seconds. This is the same. Let's go step by step and change one parameter by one. Okay, I especially make a big difference in inertia. In other words, if we have more inertia, it means that all the processes go slowly. As a result, the system reaction on a power outage is lower. The reaction speed is lower. As a result, frequency dropping, decreasing speed is lower. What is here? Okay, what do we see? The yellow one, you see how the frequency drops, and the blue one, yeah, we see this difference. And here, what do we see here? Was the frequency is rising here from, I think it's the time moment 5 seconds. It means that when we have a shortage, yes, when the shortage appear, we see here the frequency drop, and then we have the frequency restoring. What is going on? Why does this happen? Because we have this static regulator. We see that we don't have enough power, and we have its regulator reaction that we could, how to say, produce more power. But this, of course, is limited. But this coefficient, how much? Only 5% more we could produce here. Oh, sorry. So we see all the processes here with smallest inertia of 8.5 seconds. All the processes go faster. And here, all the processes go slowly, but the result is the same. The only difference is the time, yes, of the process. That was the system inertia. Okay. Go back 8 for 5 seconds. Now let's see the difference in the regulation. So this regulator, static regulator, have 3%. This one has 7%. So how much power could we produce more? Let's see what is the difference. And this is the difference. Yes, we have 7%. Yes, we could raise the frequency because we can produce more power. And this is what is going on with a 3%, yes, with a frequency. So this is the difference. Okay, what more parameters do we have here? We have, okay, let's come back to 5%, some average value. And here we could play with this reaction. This is inertia, but the same inertia, but only for the valve. Okay, we could put this in there, 5, yeah? 1 second and 5 seconds. Let's see what is the difference. You see? Five seconds. We need more time to increase the water flow. And it means that this restoration goes slowly. But all the process goes together because it's just a time, yes, of it's a time of valve move, yes, to push more water. Okay, so and then go back. So you have two equivalent schemes. You should change scheme parameters, analyze analyze scheme parameters, analyze difference in frequency deviation frequency deviation So what does it mean? Deviation. Name and value. You change. Make a print screen of frequency. Describe in few sentences. Why? Okay, I think it should be clear. You should change scheme parameters, analyze difference in frequency deviation, write in document parameter name and value. You change, make a print screen of frequency, write in document parameter name and value. You change, make a print screen of frequency. Describe in few sentences why do the curves look this. Okay, save. This is for your task. Okay. First scheme is very simple. Go next. We have scheme number 2. We have scheme number 2. Okay. So what do we have here? We have 2 power plants. Here we have, this is inertia, this is a transmission line, and this is a load. Okay, I have in this description. Okay. This is, I don't need to draw because yes, I have this one. So we have the load, we have the transmission lines. What is the idea of this scheme? Very simple. For example, if all is in balance, so these two generators produce enough power for load 1 and 2 demand. But there are some scenarios. For example, this load, yes, this load has a demand much more when this power plant could produce, and this power plant has the power more when the demand of the load number 2. It means that these generators, all his power transfer and deliver to the load 1, and what this load need more is transmitted from this power generator 2 via this transmission line. This transmission line, of course, have limits, yes, of power. How much power could we transmit here? This is one. And the second is the time. Yes, so we need time to transmit this power from here to here. And there is quite interesting to see how this more complicated, yes, power system operates. The task is the same. The only one you have one more elements that we have the transfer. Okay, I can add to this document, maybe one more correction. Transmission line, transfer limit. Okay, 1.2. Okay. Okay. And for the task number 2. Okay, so let's it be task 1. And let for you it will be task 2 to be more clear. No. Yeah. You should when nodes are different. Okay. Zero. Okay, so here for now we have a balance. Yes, PT, system in balance. Okay, so maybe I like correct, not spend. When okay, this is first of all, let's make this. Okay. Okay, let's show. This window shows what is going on in transmission line. Okay. For now, we'll see. See, we have different deviation, but it is. Let's see why we have this 5, 1, 1. 2, 1, 1.6, 5.6. Okay, yes, that's why. Yes. At the beginning, there is a small difference in this P. Okay, we don't. Okay, so yes, when everything is in balance, we see that frequency at each node is equal 15. Everything is correct. Now let's make any disbalance from a power generator side. Okay, what do we see here? Yes, overpower, because this is overpower. If we put minus, we have a deficit, which means that we have enough power. Here you could see how it drops here. Okay, so the next one. The next step is to change what is a power shortage. So for this purpose, we could add here. Okay, maybe in just PT. Okay, I need to comment that here it would be negative. Okay, negative and positive. Okay, just for you. Negative. Okay, positive. Let it be positive. Okay. Next, PSL. Should be different. Okay. This is for the second task. Okay, let's see what is in a scheme number 3. The last one, scheme number 3. All these 3 tasks are very simple because they are just, how to say, to start this modeling process, because this fourth one, the main one, to get the mark, you need to design the model from the blank list. So you have nothing, you have only these functions from these schemes, 1, 2, 3, and you need to make the scheme, and what is more, you need to design this auto frequency automation. And how good this design will be done means what mark will you get. Okay, this is a third scheme, but my suggestion, do these 3 tasks, send to me, I'll check, we'll make corrections, because this will help you to start this 4th task. That's why this basic is very important from my point of view. Okay, and the last one is when we have a generator with infinitive power. So we could produce as much as we need. Let's model. Here you could see, yeah, whatever the power shortage appear, the regulator restore the frequency because we have enough power to do this. We have unlimited power, but here you could play, yes. Okay, task 3. Task 3. 3. Unlimited power generator. Okay, this is not correct for the second. Okay. Okay. Okay, this is all what I would like to show you. The next, how to say, step is to finish these tasks. Yes, I'll send you all these schemes, pictures, this description. I put all of this. I mm, mm. I put it in Ortus and I sent all of this in email to be easier for you. And next, we'll start to discuss about how to model by yourself. What do you need? And how to analyze the results. Okay, this is all for today. Maybe you have questions. But maybe I need to mark up if you don't have enough knowledge about the control, basics of control theory, about the transfer function. It would be very useful just this to read in short in internet about these basic transfer functions. How do they look like? Because the basic function is only, there is only 5 basic functions, these transfer functions. For control theory, only 5 types. And what do they do? And how we model the process using these functions, yes. How this goes. Of course, if you need. Okay, maybe more questions. So I stop the record. Okay. Now this is screen. Stop share. Stop.